Welcome to Intro2Astro 2024.
So as Shitan mentioned, a Python package is simply a collection of code that serves a particular purpose. For example, in multiple occasions, you may want to generate, say, a list of random numbers, say a Gaussian distribution. So writing such a code in a well-packaged format, you can recall the code multiple times in multiple different projects. So having modular and reusable bits of code is the essence of writing a Python package. So there are many useful package out there you can download from, using pip or just from the internet. And today we'll go through a few of these. The first package I want to introduce is Numpy or numerical Python. This is perhaps the most fundamental package for Python. Contains a large number of mathematical operations that can be used in science, data analysis, engineering, etc. And many brilliant people have contributed to writing Numpy. So thanks to these efforts, Numpy is actually pretty efficient and pretty fast. Okay, now let's import Numpy by using this command that Shitam mentioned. Basically, you import followed by the name of the package. And if you like, you can import it as something. And this something, for example, NP here is a shorthand for the full package. So import basically tells Python that you're gonna need some of the code written in this package, and Python retrieves for your use later on. Okay, the first thing I want to introduce you to is the so-called NumPy array. So here, it's around the first cell here. So here I'm defining a Python list, which is just a list of numbers, say here 1, 3, 45, and 8. And then I'm converting this list into a NumPy array by calling np, which is again short for NumPy, dot followed by the specific function name, which is array here. And you give it a, which is the list we have defined. So now if you print out both a and a dot a subscore np, you can see it's the same list of number, but they have different type. The first one is a default list in Python, and the second one is the NumPy array. Now, why is NumPy array used? A chief reason is that arrays are much faster than lists. So it may not manifest with such a small array. Now let's try to generate a much larger array. So here I'm generating 10,000 ones and put it into a NumPy array by calling this function numpy.ones. And you can see this indeed a list of ones and the number of elements, which can be found by this command len, which stands for length, I think. You can see there are 10,000 elements. Now we can try to sum all these numbers together and see how long it takes. We can do this by calling another package called time. Let's not worry about that now. The purpose of calling time is to tell us how much the code takes between running this command and before starting the command and finishing the command. So if we don't want to sum the list as a NumPy array, it only takes about 0.2 milliseconds. However, if we do the same by using a list, then it takes a full 2 milliseconds. So there's a factor of 10 improvement if you do the same operation in NumPy array. And this is a key point why we're using array or NumPy array wherever possible. So let's look at a few other ways where you can initialize the array. You can just, give the array as a number of lists. That's what we have seen. You can also generate a series of zeros. For example, A2 here is 10 zeros, and this is the function you would use to generate that. You can also generate a two-dimensional array. Here we're just using two numbers and give it to np.0. And you can see this is basically a matrix. It can also be the case you want to generate a series of random number, which is shown here, np.random.random.random. gives you a uniform random number between 0 and 1. And another useful random number generator is random n, which stands for normal distribution. So this generates a unit Gaussian distribution centered at 0 with a standard deviation of 1. Sometimes you also want to generate a uniformly separated list. For example, here, this is np.lineSpace. Basically, the first argument here is the start of the array, 0, and 10 is the end of the array, and 20 is the number of elements you want. And you can see the output is irregularly spaced real numbers between 0 and 10. You can also use np.arange, which actually does the same, more or less the same thing, but instead of specifying the number of elements, you specify the interval between the elements. For example, here is 0.2, so you generate all the number from 0 up all the way up to 10, and the interval is 0.2. You can also generate a series of number uniform in log space. This is done by calling the log space function. Okay, so that's all about generating arrays. Let's look at how we can specify elements, or so-called slicing of array. So earlier we have generated this array called A6, and I printed its element here. Basically, it's a regular spaced array from 0 to 10. How can we specify a certain element of this array? That is done by using square bracket here, and we can change the number here. For example, 0 stands for the first element of array. So in most computing language, you'll find that 0, when indexing, stands for the first element. And 1 is the second element here. You can see this 0.52 value, so on and so forth. So 2 is the third element. Another way you can specify array is calling from the very end. For example, if you call -1, that's actually the last element of array. -2 is second last, so on and so forth. So with array, you can now directly perform mathematical operations on it. For example, you can do A6 plus 2, so all the elements now gets 2, gets an addition of 2. You can add 4 to it, 6, or times 6, whatever you want. And you can also what do you call it? You can also use array as arguments to functions. For example, np, the sign here is the trigonometrical sine function. And if you use A6 as input, you can get the sine of all the individual elements, and it's applied to all the individual elements at once. Okay, we'll talk more about plotting later. For now, let's just import matplotlib to plot some simple function. And first thing I want to show you is this sine function we have just seen. Now, x is another NumPy array. Now it's uniformly spaced between 0 and 10 with more elements. Previously, we have 10 elements, but for a smoother curve, we can give it 1,000 elements. And y is simply np.sine, the sine of x. Now we can change the input in time and see how this goes. For example, if we only have 10 elements, the curve is very jagged. Right? As we increase the number of elements, then the curve becomes smoother. Okay, so how can we show all the elements of array? This is done by using this semicolon. And we can specify a range of elements, again, using the semicolon. For example, this is shown here. This is actually from the third elements all the way up to the sixth element of the array. Actually, for Python, this is actually the fifth element of array, because for Python specifically, you call the elements up to that number by excluding that number. For other computing languages, this may not be the case. Be mindful of that. This is kind of unique for Python. Another way is you can use two semicolons. The first number here specify the starting element you want. And the second number here specify the last element. And the third number is actually interval at which you select the numbers. For example, here all it's saying is that give me the second element of array and stop at the sixth element, but only provide array at interval 2. We can also change this to 3, then only 2 numbers included. That's 2 and 5 here. Or we can use 1 to give us all the elements here from 2 to 7. Okay, so that was slicing, which is if you know which element you want, then you can use the number or the index of the elements directly. Another way you can do element selection is using mask or filtering. Here, let's generate another array from 2 to 10. There's some integer numbers. And say we want all numbers that's larger than 5. Then we can, again, use a square bracket. But now, instead of using the numbers, we directly put the conditions inside. For example, a larger than 5, then Python is smart enough to know to retrieve the elements that satisfy this condition. Actually, you can put multiple conditions here. For example, using a curly bracket, and you say you want all number that's larger than 5 but smaller than, say, 8. Oops, need this and sign for and conditions. Then, as you can see, you only get 6 and 7. All right. So another thing we can do with Python is stats. So here, let's begin with a list, with the array of random number, and we generate it through this rand_n function. And again, this number specifies that we're generating 10,000 random numbers. And if we plot it, we can see the random numbers are centered at roughly 6 with some amount of standard deviation. Now we can find the mean value of this list of random number by calling np.mean, and you just give the array again. And you can see it's pretty close to 6. And SDD stands for standard deviation. And again, we can just simply supply the function with the array and everything works. This np.cumSum is actually the cumulative sum of number. And for example, if we put a equal to 1, 2, and 3, then cumulative sum is simply as 1, 3, and 6. It's very simple. Okay. Calculus, you can also do calculus with Numpy. For example, if you want to get the derivative, the key function you want is np.gradient. Again, using our sinusoidal function as an example, you can just give the function 2 elements. The first one is y, or the variable, and x is the parameter. And you can see it successfully retrieved the derivative of the sine function as a cosine. In reverse, you can also perform integration. This is done using the np.cumSum, cumulative sum function. And you can see, again, this is what you expect theoretically. So note this function has some small difference from a purely theoretical answer, because all you're doing here is doing infinite sum. So your answer is only correct depending on how much interval you have between each array elements. Okay, I think this is something we have seen. You can also generate a 2-dimensional or even multi-dimensional array using NumPy. Okay, I think that's all for NumPy for now. Let's move on to Scipy. So earlier I mentioned that NumPy is used by engineers, software developers and scientists. Scipy, on the other hand, is, well, more or less designed for scientific operation. A number of key things Scipy can do include parameter optimization, integration, interpolation, and signal processing. Okay, let's take a look here. So in the first cell, all I'm generating is changing the y function from a simple sign to include a quadratic function of x, as you can see here. And this is what x and y looks like in a graph. So the first thing we want to do is interpolation. What is interpolation? Well, interpolation basically operates on a discrete set of data, for example, which is shown here, and tries to interpolate or specify the value between these discrete points. What do I mean by that? Let's take a look at the result. So you can see our function is only evaluated as regular intervals. We do not know anything between them. But by calling this function, which is scipy.interp 1D, and you specify that between every 2 points, you put a cubic spline to them. And this tends to smooth the data. And you can see it kind of recovers the original shape we put in. You'll find later in your scientific endeavor, this is very handy. We have sparsely sampled data. Okay. Another thing we can do with Scipy is curve fitting. Here I'm generating another x and y array, but now the y array depends on the x in this functional form, which is more or less a quadratic function of x plus a constant, and we also added in some random noise using the normal distribution. And this is what the function looks like. Again, calling Scipy, we can use this function called curve fit. What does curve fit do? Curve fit leverages the fact that you know what the underlying function should be, but you do not know the parameters specifying the function. For example, here when we generated the function, the two parameters are, first of all, 3, which is the coefficient of the quadratic term, as well as the intercept, which is 2. Now you can use curve fit to estimate both of those values. For example, let's do it again with a smaller error. So you can see curve fit actually retrieved the 2 parameters you put in pretty well. First one is 3. Again, this is the coefficient. 2 is the intercept of the function. So you know the value is not exact because we have put in some random noise here, and the estimator may not be perfectly unbiased. All right, moving on. Let's look at another data set. So here, what we get is a series of numbers, say the measurement. You do not know how these functions generated, but looking at the results, you can pretty much tell that the data can be well described by sinusoidal function. So what can we do? We can again use curve fit, and our guess is the function is specified by sinusoidal function, and we just put the sinusoidal function inside curve fit, and let's retrieve the parameters of curve fit. Let's see. So you can see Scipy curve fit does a pretty well job of modeling the data we have. There's some locations where the reproduction is not perfect, but in general, the trend is well captured by sinusoidal function. Okay, shortly before we end, another thing I want to introduce you to is Scipy has a whole list of special functions, for example, Bessel function, Legendre polynomial, and many more. So you're not expected to know what these means. I think this will come later on in your undergrad courses, your physics courses. But for now, the point I want to make is that when you encounter special functions like this, Scipy usually have them implemented. All you have to do is import these functions from Scipy. And you don't have to reinvent the view on your own. All you have to do is to call this function using Scipy. For example, the Legendre polynomial is recreated perfectly here using Scipy.
Register now on bit.ly/Intro2Astro 2024.